And welcome to 3 theorems involving proportions. My name is Sir Nigel Honeybun. You may call me Professor. This is from section 8.5 in your books. I'll be standing in for your regular instructor today. So, let's move on, shall we? Your objective for today, you will be able to apply 3 theorems frequently used to establish proportionality. This is a lovely word, proportionality. Use it, know it, love it. Theorem 65. This states that if a line is parallel to one side of a triangle and intersects the other 2 sides, it divides those 2 sides proportionally. This is known also as the side splitter theorem. In practice, it would look like this. If you have triangle ACD and BE is parallel to CD, you could call this segment AB, and the ratio of AB to BC would be equal to the ratio of AE to ED, thus creating a proportion. And it would be dividing these 2 sides proportionally. So that's an example of the side splitter theorem. Let's move on. Theorem 66 states the following. If 3 or more parallel lines are intersected by 2 transversals, the parallel lines divide the transversals proportionally. Notice the reoccurring theme. This doesn't have a fancy name like the other one, but just as easy to figure out. So say we have this diagram, and we are told that AB is parallel to CD and EF, and we have the following measurements, 10, 5, 4, and we don't know what BD is. Well, we have our ratios, AC to CE, and if that's AC, then BD to DF, and we can simply substitute the numbers. 5 over 10 equals x over 4. So we could cross multiply, because 5 times 4 equals 10 times x. If you go through all the math, you would figure out that x equals 2. Now we have a ratio of 1 to 2 that we could apply to any part. Next, we have Theorem 67. Theorem 67 states the following. If a ray bisects an angle of a triangle, it divides the opposite side into segments that are proportional to the adjacent sides. This is known as the angle bisector theorem. Now, basically, if you had an angle of a triangle and you knew that it was bisected, then you could say the ratio of this to this and the ratio of this to this would be equivalent. And we are going to use Theorem 65, which, if you recall, is the side splitter theorem, to prove this theorem. So let's move on, shall we? Here we are given that triangle ABD is a triangle, and that ray AC bisects angle BAD. And we need to prove that segment BC to CD is equal to AB to AD. Now this will come into play as we go through the proof. Pay attention. We start with our given, obviously. Move on, we can say that angle 1 is congruent to angle 2 by division, followed by, we would then draw a line through B that was parallel to AC, because of the parallel postulate, which, if you remember, states that through any given point, there is only one line that is parallel to another. We would then extend DA to intersect the parallel line at some point which we would call E, and that is because a line can be extended indefinitely. Basically, it can go on as much or as far as you want it to. So because of this, we could say that the ratio of BC to CD is equal to, or creates a proportion of ratio EA to AD because of the side splitter theorem, which, if you recall, is Theorem 65. We could then say that angle 1 is congruent to angle 3 because if we have parallel lines, then alternate interior angles are congruent. We could say that angle 2 is congruent to angle 4 because if we have parallel lines, then corresponding angles are congruent. And angle 3 would be congruent to angle 4 by the transitive property. Because up here, if you notice, we said that angle 1 was congruent to angle 2. And over here, we said angle 1 and angle 3 were congruent. So transitive, remember, this is not substitution. Substitution would be if we are putting angle 3 in place of angle 1, or if we are not, in fact, doing that. We are transitioning it from here to here, and then from there to there, which brings us to this. And then we can say that segment EA is congruent to segment AB because if we have this, which we do over here, then we have this. So if the angles are congruent, then these sides are congruent. And finally, we can say that BC over CD is equal to AB over AD because of substitution. Because remember, we had this back here. We showed that segment EA was congruent to segment AB, so we merely substituted that in. So when you're trying to prove proportions, determine what triangles they are a part of. Hopefully you enjoyed this time with me